Welcome everybody to this session about lifelike actions and reactions. My name is Nicolas Borromeo. I'm a senior software development consultant here at Unity, and I'm here with Vera Mommersteeg, who is a senior physics developer. And together we are going to talk about plenty of physics things. First, we are going to start with a little recap of the different physics offerings we have in Unity. Then we are going to talk a little bit about the news, about the latest updates we have released of those systems. And finally, we are going to talk about lifelike behaviors, meaning how to achieve believable physics, and also lifelike scale, which means how to create massive physics simulations that perform well. So let's first start with a little recap of the different physics systems Unity has right now. So we have three main physics systems. We will start describing a little bit of PhysX, which is our game object-only physics system. It's the regular, physics system we have been used for so much time. It's the most major integration of any physics systems Unity ever had, and it's the power engine for most of the games released so far of Unity. And it provides the familiar workflows you are already used to work with, rigid body, colliders, and such. We also have, for dots, Unity Physics, which also provides the familiar workflows like rigid bodies and colliders. And it is a stateless and deterministic physics engine. It being stateless supports certain gameplay mechanics like rollback determinism in a way more simpler way than other systems. And another ECS system is Havok. Essentially is a stateful and deterministic physics engine also, that being stateful allows it to support more complex simulations and larger ones. It's worth mentioning that when we talk about determinism, we are talking about single architecture determinism, because so far Burst compiler doesn't support multi-platform determinism. That's on the way. And yeah, in a moment, we are going to talk a little bit about what stateless and stateful means, but bear with me with that one. So let's first discuss a little bit about the news on the game object physics world. I will leave you with Vera, who will be talking about that.
All right. Thank you, Nicolas. So before we move on with achieving lifelike physics in your game, let's see some interesting new features that we have been implementing. Okay. So let's start up with what we've done so far. As part of an initiative to improve the PhysX integration, we have improved the performance in the following areas, starting out with the job system integration, where we have reworked the job system integration of PhysX in order to avoid job stealing and improve the load balancing across multiple workers. And this has been backported to 2022. Another thing that we've done significant work on is on the transformed system dispatch integration with physics, where we jobified the computation of our poses, when writing the data from Unity to PhysX. Furthermore, we have improved the initialization time of most of our physics components, such as colliders, rigid body, articulation body, all in 2023.3+. Last but not least, we've also added scratch buffers. It's pretty new in 2023.1 also, which should help or improve the simulation performance by allowing PhysX to avoid any temporary allocations during the simulation. All right, let's start out with the improvements in the job system integration changes. In the slide here, we can observe a 2022 LTS and 2023.1. And here you can see in a simple scene of around 4K objects, the newly improved integration. As you can see, in general, the performance was increased due to it no longer job stealing. And the problem what previously would happen is that the main thread which used to starve the workers processing most of the PhysX jobs. So now that we've reworked it, the work is better spread across between main thread and the rest of the workers. A side effect, though, about this is that if you only have a scene of only static objects, it will no longer run the simulation step, as if previously it would still run the simulation step. We found out that that is not necessary, as any queries that would need updating from the BVH, it's already it's required before the query is executed anyway, so all good. Right, so transform dispatch improvements. As we've mentioned before, we've offloaded the computation of poses of the job system. This allows us to avoid recalculating the transformation process of colliders within a game object hierarchy, where the root of the hierarchy is a rigid body and it had its transform modified. This picture compares 2022 LTS with the physics transform sync states to comparing to the 2023.1 plus tech stream where we have improved this system. All right, so those were the changes that we've done on the game object side. I will pass it now back to Nicolas, who will talk about some new features on the dots physics side.
Thank you so much, Vera. So, well, what's new in the dots physics engines? There's plenty of new changes, but the most important ones I want to discuss a little bit is first, Blob Inspector. You know you wanted, now you have Blob Inspector finally, and that means that you can also see colliders. Remember that in PhysX, in Unity Physics and Havok, colliders are essentially blob assets. We also improve essentially the API to handle runtime collider modification in those systems. And finally, we improved the joint and motors behavior. So let's discuss these changes in a little bit more of detail. You know, in the past, in ECS, if you wanted to see blob assets, you couldn't in the inspector. You were greeted with just a nice hash, and that's it. Now, instead of that, we have a nice view of all the properties of the blob asset. In this case, you can see things like the material, properties of the collider, friction, type, size, every property that allows you to easily debug your physics simulation and sim. And this is a both-way street, meaning that you won't only be able to see such properties, but you will be able to change them at runtime and see how they affect your simulation. In this case, you can see how I am increasing the size of the box collider, and it's interacted in real time your simulation. So way better tools to debug your physics systems in dots in this case. Also, we hear your pain about handling runtime modifications of colliders. For a little bit of context, every rigid body that has the same collider settings will have a shared instance of the blob asset collider, meaning that if you change the blob asset of the collider, essentially all the rigid bodies will be affected. So if you needed to make a specific rigid body unique, you needed to clone the collider, modify it, and then dispose the collider manually. So it required a lot of bookkeeping of which collider was cloned and which weren't. Now you have two very convenient APIs. You have first the isUnique API that will tell you if the collider is already cloned or not, prevent you from unintended clones, and the MakeUnique API that will make the clone for you and bookkeep that clone so you don't need to do it on your own. So it's a way more simple API to handle these situations. So having explored the news about the physics systems, now let's talk about the lifelike behaviors. And with this, I mean how we can achieve believable physics without the classic glitches that distract your user from the experience. Let's start with the classic one, tunneling. And I will describe how it is, just showing a simple example. We have the classic bullet through paper example. And you can see that it consists essentially of a very fast moving object. So in this case, I'm going into a frame-by-frame basis that's moving very fast. And you can see how the reaction differs according to the collision detection method used. Remember that in physics, you have three collision detection methods: discrete, continuous, and speculative. That setting that you find in the rigid body. So you can see how discrete fails to detect the collision, whereas continuous and speculative works flawlessly. Let's explore why this happens and how the different contact methods works. So first we have discrete, which is the cheapest of all the systems, and that works by creating or detecting the ABB of your body and detecting colliders that fits inside that ABB. So in this case, you can see that in time 1, the object doesn't have any collider around, so it keeps moving. Time 2 doesn't have any collider around, it keeps moving. And then time 3, you can see that between time 2 and time 3, several centimeters or even meters this differentiates them. That means that the object moves so fast that it skips entirely the wall. And as we do the collision after, we didn't detect a collider, and we keep moving on. So discrete is very simple, but is prone to these issues when the object moves very fast. So what you can do in that case? You can use the other collision detection methods like continuous. Continuous work by sweeping the shape of the object between the different times, between, in this case, time 1 and time 2, and time 2 and time 3. So you can see how, in this case, the sphere shape was swept no collider collision was detected between T1 and T2, and between T2 and T3, the collider was swept to the original end position, but we detected a collision before, and we just moved the collider to the time of impact. This solves the issue, but consider that it's way more costly than using plain discrete. And we have another option, which is speculative. Speculative works pretty similarly to discrete in the sense that it still uses an ABB, but this time the ABB is expanded along the trajectory of the object. So you can see how in this case we expanded the ABB between T1 and T2, between T2 and the possible T3, and then we detect the collision. So both continuous and speculative solves the issue, but when to pick which one? Because continuous is more costly than speculative, so why we should use continuous when we should use speculative? So one of the biggest differences between these two mechanisms is how they handle rotation. So continuous works by sweeping the object between the original position and the final position. But if the object didn't move at all, it only had angular motion, no movement was done, so no sweep is calculated by systems. Hence, you won't detect this example of a paddle rotating and hitting against a ball. So in this case, continuous won't work. Here is a case where you will want speculative. Speculative works by expanded the ABB, and it takes into account the angular motion. So the expanded ABB, in this case, considers the ball. So when you have, the bullet through paper problem, you need to pick between continuous and speculative, and the choice depends in a great measure according to these requirements. So speculative is better. Why should we use continuous then? Because speculative introduces another problem given how it works. So it's what is called ghost collisions. Let me exemplify this. You can see in this case a simple ghost collision, and why this happened. Essentially, you see a ball moving through a flat surface, and for some reason in the middle of the trajectory, the ball suddenly jumps. Why? Well, let's explain a little bit why this happened. Something to consider is that, again, this only happens on speculative, not on discrete and not in continuous. And also consider that Unity Physics and Havok only supports speculative. So the only one who supports discrete and continuous is PhysX. Essentially, that means that in PhysX, when you use speculative, or if you use Havok or Unity Physics, you are going to face this issue. So let's analyze why this happens. So in this case, you can see an analysis of the situation. You can see that the ball is moving against between T2 and T1 in a parallel to the surface motion. And you can see an expanded ABB, in this case, the red line. And in this case, remember that I'm exaggerating a little bit the ABB just for demonstration purposes, but also consider that the expanded ABB will not only closely fit the trajectory, but will also have a little margin to consider different ancient stuff, like, as an example, contact offset. So again, leaving that aside, in this case, we can see how we detected two bodies, B0 and B1. And for each detected body, a contact point is generated. So in this case, we have C1 and C0. And you can see that C1 looks okay. It's essentially the closest point to the ball against the body 1 is immediately below. So the contact point starts at that point. And then the normal, which is essentially the direction between the contact point and the object body, is moving upwards, meaning that we have a correct normal. Because we are traversing a flat surface, the normal should be parallel to the ground, or perpendicular, actually. So when this contact is resolved, Unity says, okay, I'm traversing a parallel to the ground surface, I'm moving parallel to the ground. So between comparing my movement vector and the normal vector, I'm not hitting that because I'm moving, just sliding in that surface. So that contact is properly detected. But the problem comes with the second body, B0. So you can see that essentially contact 0 is the closest point is essentially the corner, the little top left corner of the object. That's fine. That's effectively the closest point between B0 and TC and our object. But you can see that the normal is not right. It's, again, the direct direction between the closest point and my object. But given it has this inclined direction, That means that Unity understands that we are hitting against the tip of this square, even if we are just have another collider right next to it, and it will understand that we hit a slope. That's why our object jumps unexpectedly. You can see here another little visualization using the physics debug component in ECS that allows you to debug all this information. So that's inconvenient. What we can do? I have seen several tries of different Unity users that are not correct. As an example, reducing the contact offset, that means the minimum distance that your object needs to have in order to consider a collision, is not a good idea. Usually a little bit bigger than 0 to account for different floating point imprecisions. If you reduce it a lot, what could happen is that due to, again, floating point imprecisions, some contacts might not be detected and more tunneling happens. So reduced contact offset is not a good idea. I also seen sometimes that the bounce threshold in the physics settings is reduced for other purposes that could cause, again, contacts, unexpected bumps or ghost collisions happening. So again, don't play with very, very low bounce thresholds. Okay, what other option we have then? For PhysX, we have a nice solution, which is essentially merging the objects, because in this case, PhysX generates just one contact point per body detected inside the ABB. So if we merge B0 and B1, we will end up with just one contact point, which will be C1 in this case, the one we have. Consider that in the seam between B0 and B1, we will be having two edges, weld them to avoid having small imprecisions when you have two close objects. Of course, that is a neat solution that will work, and feel free to merge your entire static scene. That should be fast enough, even if they are mesh colliders. That's safe to do. But when you can't do that, when you can't merge, or when you use Havok and Unity Physics, this won't work. Because in Havok and Unity Physics, the problem is that even if you merge, we generate one contact point per primitive inside the ABB. So if inside the ABB you have a sphere collider or a box collider, you will have one contact point for them. But if you have a mesh collider, you will have one contact point per each primitive. So in this case, each triangle or each quad inside. So even if B0 and B1 is merged, it will still generate two contact points, in this case C0 and C1, in Havok and in Unity Physics. So, okay, Unity Physics has this kind of merging pseudo solution. When that doesn't work, what you can do? Well, consider that essentially all physics engines are prepared to handle kind of a lot of edge cases. So they are very, very generic tools. And that means that sometimes certain cases that we don't care about are considered, and these kind of things happen, cause collisions. So what you can do instead, you need to adapt this physics system to your game. You have no escape of that in the physics systems. So in this case, what you can do is to hook up an event to the, and in this example, the physics.contactModify event. That is an event that works in PhysX. And essentially, it allows you to receive a native array of all the contacts that were detected. This happens before the contact solver receives the contacts, meaning that you have the chance to modify them before the collisions happens. So in this case, what you can do with this, you can do whatever you want. You can modify the normal, you can modify the position, you can modify the contact distance, you can even ignore the contact if you really don't want to have it. So it's a very, very powerful tool. And consider that here you are receiving a native array, meaning that that can be easily be worked in shops, if you can. So that's a very good API to use. Consider also that this API works, we have another API for continuous detection, meaning that if you have contacts that happen through CCD, you will need to use physics.contactModified event CCD. We have two events for different contact detection systems, but just hook up to both of them and handle the collisions that way. For Unity Physics and Havok, we have shops. We have the eye contact shop that allows you to essentially, detect the collisions and analyze them in parallel in shops. This is a special kind of shops that requires some more data other than just scheduling. As an example, you can see that in order to schedule an instance of this shop, we need a simulation singleton and the physics world singleton, but you can use this API easily to get that information. So we have several events that you can hook up and modify in the middle of the simulation. This is just one example of how you can modify the systems. So great, now you have a way to modify your physics simulation. What you can do with that now? Again, you have several approaches that depends on what you want to do. So one simple approach will be the contact discard approach. This works by just simply discarding the contacts that you don't want. So one possible criteria to discard contacts is to discard contacts that are not parallel to the surface you hit. That will be a very good and simple criteria in the case of the object moving through a flat surface. So in the image, you can see three lines: the green, the blue, the white, and the red one. The blue one represents the normal of the surface the black ball is traversing. And the white one represents a contact that passed our test, because in this case, you can see that the contact has a normal that is parallel to the surface. The red one is a contact that was discarded because, again, the angle between the normal of the surface and the contact were too different. So in this case, you can see how we eliminated the unexpected bump. Of course, this is a very, very broad and simple criteria that won't cover every case. As an example, one case that this doesn't cover is the non-parallel contact image you see there. You can see that the contact that is generated in the tip of the triangle is pointing upwards, meaning that it's what we expect, but it is not parallel to the surfaces of the triangle. So this will discard this contact, and a tunneling could happen in this situation. So we can refine a little bit the criteria to only discard contacts that lies in edges that are connected to other bodies. You will need to manually track that. We don't have any tool to do that, so you need to analyze your geometry to consider these cases. Again, this might not consider all cases, and this is just one solution to specific problems. You will need to adapt the simulation to your different problems. Another useful thing about discarding is that you can discard certain unwanted contacts like back face contacts. In this case, I have this kind of ball that is moving directly to the tip of the bottom left part of this quad. And you can see how a contact is generated again against the bottom face. Because even if the face of the object is the back face, it will still generate a contact. Consider that this is a mesh collider, not a regular collider. I'm just considering a regular cube collider. So you can discard back face contact this way. Again, I mentioned that contact discard might not be a good idea all the times. And why? Because it can generate tunneling. So another approach will be to tweak the contact to change the normal of the contact. So that is what we can see in the contact distance scaling approach. In that approach, we modify the normal of the contact against the contacts that, in this example, falls the previous criteria, the contacts between the edges of different colliders. And in this case, we just modify the normal to be parallel of the surface to better reflect the actual situation we have here. So modify the normal is also a good idea, and in this case, you fix this issue. And finally, for Havok, we have a built-in solution called contact welding. This is, again, something that you need to enable, and that's it. Havok solves the problems for you. You can see that even if the normal is still there, the contact is still there, there's no unexpected bounces. That's because Havok essentially analyzes every contact, analyzes the motion of our object, and determines what will be an ideal reaction or contact. So you can discard, you can modify the normals, or you can use Havok's solution. Neither of these three solutions will solve every case. You will always need to handle that due to how the physics systems work. So, and again, here I'm also using the different debuggers tools. Remember that we have very powerful debugger tools. In the case of Havok, we have a Havok-specific tool for debugging that allows you to see all these contacts. For, again, Unity Physics, you have the debug physics contact something component. And in the case of PhysX, you have tools. In this case, I just used debug draw line in the physics.contact events to draw those lines, but you can also use other embedded tools we have out there. So having said that, I will leave the stage to Vera, who is going to talk about lifelike scale.
All right, thank you. Right, now that we've discussed how to achieve lifelike physics behaviors, we also still need to care about scale. So how do we achieve these scales? There's a couple ways we can do this, but first, we need to decide something before we start going into that. And that is that we need to choose our physics system. And there's two things to consider, stateful and stateless. Both have their advantages, disadvantages, and use cases. Right. So some of you might have heard the term before here. Generally, when we talk about unity physics and Havok Physics, you've heard it before. But the biggest factor to know about stateful is that we, when we're making a simulation stateful, is that we cache the physics simulation state. This implies that we make a copy of the physics world, and it will not simulate identically to the original world unless all the internal simulation caches are also copied. So in cases where this means that in cases a stateful simulation, it can help with performance because everything is already cached. A very common case, as you can see here, where stateful simulation is useful for is stacking. Because we are caching the contact points from the previous frame, it can help in stabilizing the stacked objects by reusing the soft contacts when they are in a state of resting. However, that doesn't mean that stateless is out of the run. Stateless has its benefits too, especially in the world of networking, where if we want to roll back and forward to physics states, we need a deterministic simulation. And if we want that, we need a stateless simulation loop to have the most current data instead of a cached state. That's the reason why in a stateless simulation, you might see small artifacts, as you can see here, because we didn't cache the contact points from the previous states. And that is because we don't retain any of this information from the previous states, and we will have to recalculate the contacts in order to resolve the impulses between the points each time you simulate. The main advantage for stateless is the flexibility it offers. Because we're not caching any of the state data, this simplifies the simulation pipeline, and it makes it much easier to modify and control the different use cases, such as forward or rollback in a multiplayer environment. Right. Now that we have talked about stateful and stateless, we have figured out what we want. The next thing that you tend to deal with when you have a large world is world origin problems. So when we deal with large worlds, it's a common issue due to them living far away from the world origin. A couple of types of artifacts will start to manifest as you move further and further away from the origin, such as simulation instability. We all know this, we all would do it, and this is how it looks. We know it, we love it, not really. Right, so the most notable effect of objects moving far away from the scene origin is the loss of floating point precision, as more and more of the bits will be used to represent the exponent part of the floating point number. One of the main symptoms of this is the positional rotational jittering, as you can see here. Usually for simple cases with like some box stacking or some trivial joint setup, you can go as far as like 30K units from the origin. But if you start using like more complex cases, you can already start seeing problems at like 10K units. So it's recommended to not reach those distances in the first place. So let's see how we can deal with this. So one way to tackle this issue is we can split our large world into multiple pieces or chunks to stream in and out as necessary. Once we are done with dividing our world, it becomes defined as an area that can fit a fixed number of chunks. By using this approach, we can now offset all currently loaded chunks as such that the player is always within the same area of space, regardless of which chunk it enters. As you can see here, in the slide, we mark the transition borders for moving all loaded chunks here in green. Once the player passes into the new chunk and exits the marked area, the currently loaded scenes will be moved using transform jobs. A key factor to note here is that we will need to preserve the state of all dynamic physics objects when doing this. And that is a good thing to keep in mind, as having to apply transformations to a large amount of objects definitely can cause some hiccups. So that's something to keep in mind. As such, when dealing with this kind of approach, you'll need to find a good balance between object density inside chunks and performance. All right. So as I mentioned before, we can use transform jobs in order to move a large quantity of objects around in our scene. And in this slide, we can see a very simple example of how to achieve this using transform jobs. One important thing to note is that you will have to convert from a managed array to a transform access array before any of such operations can be executed. So with regards to the case presented on our previous slides, this means that for every chunk, you will have to manage these arrays of transforms yourself. Right, since we're talking about transform, this is a very known one. Let's take a look about transform synchronization, as this tends to end up being an issue with almost all large simulations. All right, so when we talk about transform synchronization inside Unity, we refer to writing transform component data into the physics SDK. That's what it means. So in the project settings window under the physics category, we can find a checkbox you probably know about called autosync transforms. And having this checkbox enabled simply means that when we modify the transform of a game object that has a rigid body or collider component on it, we will attempt to write all transform changes to the physics scene. This operation will happen for any subsequent changes to such transforms. We recommend disabling this checkbox as it will ensure that we only write transform changes to the physics scene right before simulates. It should be by default disabled, but check in older versions it might be still enabled. So make sure to check that it's off. But yes, as you can see on the slide, the two profiler captures show the amount of overhead with autosync transform on and off. If you do need, however, you say, oh, I still need the sync transform, but you want some more control, there is an API, physics.synctransform, that you can use after you are done modifying the game object transform that you are interested in. Another thing to mention here is that you should try avoid deep hierarchies. We all know, but it has to be said, as they are harder to transform dispatch to split into jobs. This is because the transform system in general will try to dispatch a scene root and all its children into a single job. All right, so batch queries. We all know that in a large world, you can end up having a high quantity of queries necessary when dealing with large-scale simulations. This can often be seen in games belonging to survival genre or VR experiences, where in some cases they rely heavily on queries to figure out the state of the world. This can easily impact the target frame time of such experiences. And a way to reduce the performance overhead would be to use the batch query API. All right, let's get into it. So this API is designed to deal with a large number of queries by forming batches and executing them off the main thread. Even on a small scene of just a bunch of rotating cubes using raycast, we can observe a difference using batch queries. And we can see on the slide here, we gain around a 50% speed up during the cube rotation and raycast update. So that's pretty good, even for a very simple case. However, we do end up with extra time spent in late update here, as we have used that point to process the raycast results in this example. So one last thing also to mention, in this case, we're talking about the raycast command, but there's several other types that you can use, such as overlap commands and shapecast commands. All right, so how would you start doing this? So if you look here, we can observe a very simple example of how you would schedule a set of ray commands from the aforementioned scene. As you can see here, we create a command per ray and then schedule the batch. An important detail to note here about this API is that as of Unity 2023.3 and later, all commands that execute on the same physics scene should be stored in a continuous manner in the array. By doing this, you avoid the underlying physics scene being fetched repeatedly by the batch query scheduling. We are considering backporting this optimization to an older RTS version, so look forward to that. We're working on it. All right, we've dispatched our batches, we're all happy. Now we are fetching the results. So in this example, we simply draw a line for each result after syncing our query jobs. However, you can process the data at a later time rather than a late update. One use case could be to process the result during the next frame. allowing more time for a query just to complete. For example, if you have a very large quantity of queries, allows you to spread it a bit more. So, all good. Another thing to note is that processing these results on main thread is not a requirement, as data can be extracted from the results array of main thread, with the caveat that the access to the raycast hit collider properties is restricted. That's not thread safe. Don't do that. Instead, you have to rely on the instance ID to figure out if there's a hit occur or not. So that's a little note. All right. Let's move on to another fun one, the contact events. Nicolas already talked a bit about it, but let's go out from the approach of scalability now. Namely, the overhead of processing a large number of contact events every frame. This can easily lead to your application being bottlenecked by a large number of collisions events being fired on mono behaviors that implement, you all know it, the on-collision enter, exit, and stays. All right. So, rather than making use of the on-collision enter, exit, and stay on individual mono behaviors, you can instead use the PhysX contact event API to process contact pairs in parallel using jobs. In order to use this feature effectively, you will need to turn off invoke collision callbacks in your project settings, very important, under the PhysX category. By doing so, it ensures that the PhysX integration does not dispatch any events to mono behaviors implementing on collision, enter, exit, and stay. As you can see on the slide, the API will return an array of body pairs, which can be used to directly fetch the respective rigid body, articulation body, collider components when executing on the main thread. Alternatively, you can use jobs in order to process the provided contact array of main thread. But once again, do note you have to use the instance ID inside the jobs rather than the C# component objects, as those are not thread safe. We plan in the future to allow at least some part of the PhysX component API be thread safe, but not yet. So use instance ID. Okay. You all know it, but it still has to be repeated. Now that we've covered contact events, let's take a look at the impact of having a large number of actors in your world. The first step in figuring out the impact of our actors should be to take a profiler capture. All right, so after we've taken our profile capture, we can see a detailed breakdown of what's happening during a simulation step in the Profiler Physics module. Within, we can see how many actors are present in the physics scene and their state. We can use this information to, for example, attempt to reduce the overlaps by simplifying the layer collision matrix. One thing to mention is that in 2023, we are working on speeding up some of these runtime filtering on collision-based layers, so that should be good. All right, so generally reducing the number of active dynamic body is what is actually needed for your simulation to run good. That's generally the good rule of thumb and should just improve your performance. So, an important thing to note is that dynamic bodies marked as kinematic are still part of the simulation. As a result, their poses will still be read back into the Unity's transform system after each simulation step. This overhead comes on top of any other interactions they might have with other dynamic bodies during the simulation step. Another thing to be aware of is that currently there's no way to disable the rigid body component, we know, bar disabling the game object it resides on. We are planning on handling this limitation in the future, but meanwhile, you can work around the issue by separating graphics representation of your objects from the physics one. In practice, this means that all physics components will exist on separate game objects, so that is something to be aware of. All right, and now we're at some miscellaneous stuff. Last but not least, there's a couple of small items that are just good to go over in your project to improve in performance and scale your project. I have to say it again, deep hierarchies in Unity generally is something to avoid due to the transform recomputations as mentioned on the other slides of the sync transforms. Avoid any empty on-collision enter, exit, and stay callbacks in your mono behaviors, as having those methods in your script will still result in being called from native. So please remove those. Reuse collision instances on callback, since when on collision callbacks are being called, each call will generate a collision instance unless reuse collision instant callbacks under the physics status is being turned on. This allows us to reuse the same instance across each callback. If you don't do that, the collision instance will be allocated on the heap, causing a garbage collected. So easy fix. Right. This is also an easy one. Use the non-allocating versions on the physics APIs, such as physics raycast non-alloc, or all the other allocs, just to avoid allocating managed memory unnecessary. And mesh colliders. Sometimes we gotta use them, there's no way around it, but try to use primitive colliders if you can. However, if you do need mesh colliders, then it's best to pre-bake them by setting the pre-baked collision meshes in the player settings. This will, however, increase the application size, so do note that. And then also enable all options when cooking collision meshes in order to optimize your resulting geometry. Always good. And last but not least, on the Delft's physics sides, please don't move or destroy static objects. Please don't, as that will cause a large performance hit on the project due to it having to recompute the BVH3. We are currently working on addressing this limitation in Unity Physics, but we're not there yet, so please don't do that. All right, so if you want to get involved, please don't hesitate to reach out through our physics or ECS forums, or share your feedback regarding the roadmap. Post whenever you want. And thank you for joining us. If you have any questions, we will be available at the expert booth, so you can just approach us. So feel free to come there.